Tonight, we're going to explore one of the strangest mysteries at the edge of our solar system. Beyond Neptune, there's a vast ring of icy worlds called the Kuiper Belt. Thousands of frozen objects orbit out there, leftovers from the birth of the solar system. But here's what doesn't make sense. The belt just stops. Not gradually, not slowly, thinning out the way you'd expect. It drops off sharply, almost like something sliced through it. The material that built the planets should have extended much farther. There's no obvious wall, no barrier, nothing visible that would cause this sudden emptiness. And yet, beyond a certain distance, the objects almost vanish. Something carved an edge into the outer solar system, and after decades of searching, we still don't know what did it. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you probably already know, or at least think you know. Our solar system has 8 planets, 4 rocky worlds close to the Sun: Mercury, Venus, Earth, Mars, then 4 enormous gas and ice worlds farther out: Jupiter, Saturn, Uranus, Neptune. Beyond Neptune, there's Pluto, which most people still think of as the 9th planet, even though it was reclassified as a dwarf planet in 2006. And after Pluto, most people assume there's just empty space, a cold, dark void stretching endlessly until you reach the nearest star. But that's wrong. Not slightly wrong. Dramatically, fundamentally wrong. Because beyond Neptune, the solar system doesn't end. It opens up into a vast frozen wilderness that most people have never heard described in any real detail. A region filled with thousands of icy worlds, some of them enormous, most of them ancient, all of them carrying information about the earliest days of our solar system's existence. This region is called the Kuiper Belt, and understanding what it is, where it came from, and why it appears to end so abruptly is one of the most fascinating puzzles in modern planetary science. To understand the Kuiper Belt, you first need to understand how our solar system formed. Because the story of the Kuiper Belt is really the story of the solar system's birth. And that birth was not a simple, clean process. It was messy, violent, and profoundly complicated. About 4.5 billion years ago, there was no solar system. No Sun, no Earth, no Jupiter, no Pluto. There was only a vast cloud of gas and dust floating in interstellar space. This cloud was made mostly of hydrogen and helium, the 2 lightest elements left over from the Big Bang. But it also contained heavier elements: carbon, oxygen, nitrogen, silicon, iron, elements that had been forged inside earlier generations of stars and scattered into space when those stars died. This cloud of material is called a solar nebula. At some point, something disturbed the cloud, perhaps a shockwave from a nearby supernova explosion, perhaps a gravitational nudge from a passing star. Whatever the trigger, parts of the cloud began to collapse under their own gravity. As the cloud collapsed, it spun faster and faster, the way an ice skater spins faster when pulling their arms in. The spinning flattened the cloud into a disc shape, like a cosmic pizza made of gas and dust. At the center, where the material was densest and hottest, the sun ignited. Nuclear fusion began, and our star was born. But around it, stretching out for billions of kilometers, the rest of the disk remained. This was the protoplanetary disk, the raw material from which everything else in the solar system would be built. Here's where things get crucial for understanding the Kuiper Belt. The protoplanetary disk was not the same temperature everywhere. Close to the young sun, the disk was blisteringly hot, Temperatures could reach thousands of degrees. At these temperatures, only materials with very high melting points could survive as solid particles. Metals like iron and nickel, minerals like silicates. These dense, rocky materials clumped together near the Sun, eventually building the 4 rocky planets: Mercury, Venus, Earth, and Mars. But farther from the Sun, the disk was cooler. And beyond a certain distance, a critical threshold called the frost line, or the snow line, temperatures dropped low enough for volatile compounds to freeze into solid ice. Water vapor became water ice. Ammonia became ammonia ice. Methane became methane ice. Carbon dioxide froze solid. This frost line sat at roughly 2.5 to 3 astronomical units from the Sun, roughly around where the asteroid belt is today. Beyond it, there was suddenly a lot more solid material available to build things. Ice is abundant in the universe. Hydrogen and oxygen are 2 of the most common elements, and water ice forms easily in cold environments. So beyond the frost line, the protoplanetary disk was richer in solid particles. There was more raw building material out there, and this material could clump together into larger and larger objects. Close to the Sun, rocky particles clumped into rocky planetesimals, small rocky bodies a few kilometers across, which eventually collided and merged to form the rocky planets. Beyond the frost line, icy particles joined the mix, and the planetesimals grew faster because there was more material to work with. These icy and rocky planetesimals grew into massive cores heavy enough to gravitationally capture enormous envelopes of hydrogen and helium gas from the disk. That's how Jupiter and Saturn formed. They started as solid cores of rock and ice and then wrapped themselves in thick blankets of gas, becoming the gas giants we see today. Uranus and Neptune formed farther out still, where the disk was thinner and growth was slower. They built solid cores of rock and ice, but couldn't capture as much gas before the disk dissipated. That's why they're smaller than Jupiter and Saturn, and why they're classified as ice giants rather than gas giants. Their interiors contain more water, ammonia, and methane than hydrogen and helium. But here's what's important for our story. The process of building planets didn't use up all the material in the disk. Not even close. Beyond Neptune's orbit, the protoplanetary disk continued. It extended outward for billions of kilometers. And in that outer region, the disk was thin. The material was spread across an enormous volume of space. The individual icy particles and small bodies were far apart from each other. Collisions were rare. Growth was slow, agonizingly slow. Out here, far from the Sun, icy planetesimals formed and grew, but they never had enough time or enough material packed densely enough to build a full-size planet. They got stuck at intermediate sizes. Some grew to hundreds of kilometers across. A few reached over 1,000. But none of them became a true planet. They are the leftovers. The construction debris from the solar system's formation. And they've been sitting out there, frozen and ancient, orbiting in the darkness for 4.5 billion years. These are the objects of the Kuiper Belt. The idea that a belt of icy objects might exist beyond Neptune is not new. In fact, scientists predicted it decades before anyone found the first object. In 1930, the same year that Clyde Tombaugh discovered Pluto, an American astronomer named Frederick Leonard speculated that Pluto might not be alone out there. He suggested that Pluto could be just one of many trans-Neptunian bodies, and that there might be a whole population of objects in that distant region waiting to be found. Leonard didn't have evidence. It was more of an educated hunch based on the way the solar system was structured. If the inner solar system had a belt of rocky debris between Mars and Jupiter, the asteroid belt, then why shouldn't the outer solar system have its own belt of icy debris beyond Neptune? In 1943, an Irish astronomer named Kenneth Edgeworth took the idea further. He argued that the outer region of the protoplanetary disk would have been too thin and too spread out for the material there to condense into a large planet. Instead, he proposed the material would have formed a large number of small, icy bodies, a reservoir of frozen leftovers from the solar system's formation. Edgeworth published his ideas in academic journals, but they didn't attract much attention at the time. Then, in 1951, the Dutch-American astronomer Gerard Kuiper published a paper in which he also discussed the possibility of a disk of icy bodies beyond Neptune. Kuiper's reasoning was similar to Edgeworth's. The material in the outer disk wouldn't have had enough density to form a planet. Instead, it would have remained as a collection of smaller objects. Ironically, Kuiper also suggested that Pluto's gravity might have scattered most of these objects away, leaving the region relatively empty. He was wrong about that part, but his name stuck. The belt was named after him. Some astronomers preferred to call it the Edgeworth-Kuiper Belt, to give credit to both scientists, but most people simply call it the Kuiper Belt. For decades after these predictions, the Kuiper Belt remained purely theoretical. Nobody could find any objects out there besides Pluto. This wasn't surprising. Objects in the outer solar system are incredibly faint. They're small, they're dark, and they're extraordinarily far away. Sunlight out at 40 or 50 astronomical units is incredibly weak. An object at 50 astronomical units from the Sun receives only 1/2500th the sunlight that Earth receives. These objects are essentially frozen in permanent twilight, reflecting barely any light back toward Earth. Finding them requires large telescopes, sensitive cameras, and enormous patience. You have to stare at the same patch of sky over multiple nights, looking for something that has moved very slightly against the background of distant stars. It's painstaking, difficult work, and for years it yielded nothing. Then, in 1992, everything changed. Two astronomers, David Jewett and Jane Liu, working at the Mauna Kea Observatory in Hawaii, discovered a faint object beyond the orbit of Neptune. It was designated 1992 QB1 and later officially named Albion. This small, icy body orbited the Sun at a distance of roughly 44 astronomical units. It was only about 160 kilometers across, tiny by planetary standards, but its discovery was monumental. It was the first confirmed Kuiper Belt object found after Pluto. The belt was real. The predictions of Leonard, Edgeworth, and Kuiper had been vindicated. The discovery opened a floodgate. Once astronomers knew what to look for and where to look, they started finding more objects rapidly. Within a few years, dozens were known, then hundreds. Today, we've confirmed well over 2,000 individual Kuiper Belt objects, and estimates suggest there could be hundreds of thousands of objects larger than 100 kilometers in diameter out there, with possibly trillions of smaller ones. The belt extends from roughly 30 astronomical units near Neptune's orbit out to about 50 astronomical units from the Sun. That's a huge region of space, To put it in perspective, Earth orbits at 1 astronomical unit from the Sun. Neptune orbits at about 30. The Kuiper Belt stretches from Neptune's orbit outward for another 20 astronomical units. If you could somehow compress the distance from the Sun to Earth into a single step, you'd need another 20 steps beyond Neptune to cross the Kuiper Belt. And the objects within it are spread incredibly thin. The Kuiper Belt is vast in area, but its total mass is surprisingly small. All the Kuiper Belt objects combined have a total mass of only about 1/10 the mass of Earth. Some estimates place it even lower. That might sound like a lot, but consider that the asteroid belt between Mars and Jupiter has a total mass of only about 4% of the Moon's mass. The Kuiper Belt is more massive than the asteroid belt, but it's still remarkably light for such an enormous region. Within the Kuiper Belt, astronomers have found some genuinely impressive worlds. Pluto, with a diameter of about 2,370 kilometers, is the most famous, but is far from alone in terms of size. Ares, discovered in 2005, is slightly smaller in diameter than Pluto, but significantly more massive. Its discovery was actually one of the key reasons Pluto was reclassified as a dwarf planet, because Ares proved that Pluto wasn't uniquely large in the outer solar system. There were other objects out there comparable to it. Marke is another large Kuiper Belt object with a diameter of roughly 1,430 kilometers. Haumea is elongated and rapidly spinning, completing a full rotation in just under 4 hours, making it one of the fastest rotating large objects in the solar system. Haumea even has a ring around it, one of the most surprising discoveries in recent outer solar system research. These dwarf planets are fascinating worlds in their own right. Pluto, visited by the New Horizons spacecraft in 2015, turned out to have mountains made of water ice, vast plains of frozen nitrogen, a thin atmosphere that expands and contracts as Pluto moves closer to and farther from the Sun, and a surprisingly complex geological history. Its large moon Charon is tidally locked to Pluto, meaning the two always show the same face to each other. They orbit a common center of gravity that sits between them in empty space, making them more like a double dwarf planet system than a simple planet and moon. But here's what you really need to understand about the Kuiper Belt, and this is the part that most popular descriptions skip over entirely. The Kuiper Belt is not one uniform ring of objects. It's not a smooth, even distribution of icy bodies orbiting peacefully in a flat disk. It's far more complicated than that. When astronomers mapped out the orbits of Kuiper Belt objects, they discovered something unexpected. The belt has distinct populations, separate groups of objects with very different orbital characteristics. And understanding these populations is essential to understanding why the belt appears to end so suddenly. The first population is called the Cold Classical Kuiper Belt. These objects orbit between roughly 42 and 47 astronomical units from the Sun. Their orbits are remarkably calm. They move on nearly circular paths with very low eccentricities, meaning their orbits are almost perfectly round. They also have very low inclinations, meaning they orbit close to the ecliptic plane, the flat disk defined by the orbits of the major planets. These cold classical objects are thought to be fossils. They've been sitting in roughly the same orbits for 4.5 billion years, undisturbed since the solar system's earliest days. Nothing has significantly altered their paths. They formed where they are, and they've stayed there ever since. Their surfaces tend to be distinctly reddish in colour, which suggests they're covered in organic compounds that have been processed by billions of years of exposure to cosmic radiation. Cold classical objects are also often found in binary pairs, two objects of similar size orbiting each other as they orbit the Sun. This is significant because binary pairs are fragile. Any strong gravitational disturbance would have torn them apart. The fact that so many cold classical objects still have companions tells us that this region of space has been remarkably quiet and undisturbed for an extraordinarily long time. The second population is called the hot classical Kuiper Belt. Don't be confused by the names. Hot and cold here don't refer to temperature. They refer to orbital dynamics. The cold population has calm, low-energy orbits. The hot population has excited, high-energy orbits. Hot classical objects can be found in the same general region as the cold classical objects, but their orbits are different. They have higher eccentricities, meaning their orbits are more elongated and elliptical. They also have higher inclinations, meaning their orbits are tilted relative to the ecliptic plane, sometimes by 20 or 30 degrees. Some hot classical objects swing far above or below the plane in which the planets orbit. These excited orbits tell us something important. Something stirred these objects up at some point in the past. They didn't form on these tilted, elongated paths. They were pushed onto them by some gravitational influence. And as we'll explore shortly, that influence was almost certainly Neptune. The hot classical population also looks different from the cold classical population. Their surfaces tend to be less red, their size distribution is different, and binary pairs are much rarer among them. All of this suggests that the two populations have different histories, possibly different origins, even though they overlap in physical space. The third major population is the resonant objects. These are Kuiper Belt objects whose orbits are locked into mathematical relationships with Neptune's orbit. The most famous group is the Plutinos, named after Pluto because Pluto is the most prominent member. Plutinos orbit in a 3-to-2 mean motion resonance with Neptune. This means that for every 3 orbits Neptune completes around the Sun, a Plutino completes exactly 2. This isn't a coincidence. It's a direct consequence of gravitational physics. When 2 orbiting bodies have orbital periods that form a simple ratio, the gravitational interactions between them reinforce each other in a regular, repeating pattern. This can either destabilize the orbit, kicking the object out, or stabilize it, locking the object into the resonance permanently. The Plutinos are locked in. They've been trapped in this 3-to-2 resonance for billions of years. Pluto's orbit actually crosses Neptune's orbit in terms of distance from the Sun. At its closest point, Pluto comes as near as roughly 29.5 astronomical units from the Sun, which is actually inside Neptune's orbit. At its farthest point, Pluto reaches about 49 astronomical units. You might think this means Pluto and Neptune could collide, but the 3-to-2 resonance prevents it. The gravitational dance ensures that whenever Pluto is at its closest to the Sun and theoretically crossing Neptune's path, Neptune is always on the other side of the solar system. They never actually come close to each other. The resonance acts like a protective mechanism, keeping them forever separated in their orbital timing. There are other resonances too. Objects in the 2-to-1 resonance complete 1 orbit for every 2 of Neptune's. Objects in the 5-to-3 resonance complete 3 orbits for every 5 of Neptune's. These resonant populations are scattered throughout the Kuiper Belt, each locked into its own specific mathematical relationship with the giant planet that dominates the outer solar system. And this is where the story starts to deepen. Because when scientists first began mapping the Kuiper Belt in the 1990s and 2000s, they expected to find a structure that made intuitive sense. The protoplanetary disk extended well beyond Neptune. Material should have existed out there in gradually decreasing density as you moved farther from the sun. The belt should have thinned out slowly and smoothly, becoming sparser and sparser over enormous distances, eventually fading into the truly empty space between the stars. That's what a simple model would predict. And for the inner portions of the belt, from about 30 to 47 or 48 astronomical units, the observations roughly matched expectations. Not perfectly, and the distinct populations complicated the picture enormously, but at least there were objects out there where scientists expected to find them. But then, something strange emerged. As surveys pushed deeper, as telescopes became more powerful and searches became more thorough, astronomers noticed a pattern that didn't fit the simple model at all. Beyond about 48 astronomical units, the number of objects didn't just gradually decline, it dropped off sharply, dramatically. The fall was so steep and so sudden that it almost looked like someone had drawn a line in space and erased everything beyond it. This was the first hint of what some astronomers would come to call the Kuiper Cliff, a sharp boundary in the distribution of classical Kuiper Belt objects. A place where the population doesn't just thin out but appears to collapse. This was puzzling. There was no obvious physical reason for such a sharp edge. No massive planet sitting at 48 astronomical units sweeping the region clean. No visible barrier or boundary. The protoplanetary disk should have extended well past this distance. Material should have been there. And yet, the objects were largely absent. Not entirely absent, as we'll see, because scattered and detached objects do exist far beyond this boundary. But the main, dynamically stable population, the cold classical belt, the bread and butter of the Kuiper Belt, appeared to simply end. The classical belt didn't fade. It stopped, and nobody could say why with certainty. This is the mystery at the heart of our story. The Kuiper Belt, that vast frozen archive of the solar system's earliest material, appears to have a sharp outer edge, not a wall, not a physical barrier, but a dramatic, measurable decline in the number of objects living on stable, well-behaved orbits. The belt is rich and populated on one side of this boundary and strikingly empty on the other. Something created this edge. Something carved the outer limit of the classical Kuiper Belt. Was it the physics of planet formation itself, with the disk simply running out of material at a certain distance? Was it Neptune, whose gravitational influence has reshaped so much of the outer solar system? Was it an encounter with a passing star billions of years ago that stripped the outer disk away? Or is it something else entirely? Something we haven't considered yet? To answer these questions, we need to understand how Neptune shaped the Kuiper Belt. Because Neptune isn't just the outermost planet, it's the architect of the outer solar system. And its influence on the Kuiper Belt has been more profound, more transformative, and more violent than most people realize. Neptune sits at the doorstep of the Kuiper Belt, orbiting at about 30 astronomical units from the Sun. That's roughly 4.5 billion kilometers. And while Neptune isn't the most massive planet in our solar system, Jupiter claims that title with about 318 Earth masses, Neptune's position makes it the single most important gravitational influence on everything in the outer solar system. In physics, the strength of gravity drops off with the square of the distance. That means proximity matters far more than raw size. Jupiter is enormous, but it orbits at just over 5 astronomical units from the Sun. It's a long way from the Kuiper Belt. Neptune, with about 17 times the mass of Earth, sits right at the belt's inner boundary. It's the nearest giant planet to all those frozen worlds. Every Kuiper Belt object, whether it's a tiny chunk of ice a few kilometers wide or a dwarf planet the size of Pluto, feels Neptune's gravitational pull. Every orbit in the outer solar system has been touched, shaped, or outright rearranged by this distant blue world. And to understand how Neptune sculpted the belt into the complex, divided, strangely truncated structure we observe today, you need to understand one concept more deeply than we touched on earlier: orbital resonance. Because resonance isn't just a neat mathematical coincidence, it's the mechanism through which Neptune literally reached into the belt and moved objects around. It's the fingerprint that Neptune left across the outer solar system. And it's the evidence that something truly dramatic happened out there billions of years ago. An orbital resonance occurs when two objects orbiting the same central body, in this case the Sun, have orbital periods that form a simple numerical ratio. We talked about the 3:2 resonance earlier, where Pluto and the other Plutinos complete exactly 2 orbits for every 3 that Neptune completes. But let's go deeper into why this matters. Imagine 2 cars driving on a circular racetrack. One car is in an inner lane, moving faster. The other is in an outer lane, moving slower. Most of the time, the 2 cars don't interact much. They pass each other at different points around the track, and the gravitational effects, to extend the analogy, average out over time. But if their speeds are related by a simple ratio, something special happens. They start encountering each other at the same points on the track over and over again. Every time the faster car laps the slower one, the encounter happens at the same location. This means the gravitational pushes and pulls don't average out anymore. They accumulate. They build up. Over millions of years, these repeated, synchronized interactions can dramatically change an object's orbit. In some cases, the resonance destabilizes the orbit, pumping up its eccentricity until the object is ejected from the region entirely or sent crashing into a planet. In other cases, the resonance stabilizes the orbit, locking the object into a specific path that protects it from close encounters. The 3:2 resonance with Neptune is a stabilizing one. Objects trapped in this resonance are actually safer than objects nearby that aren't in resonance. That's why Pluto can have an orbit that technically crosses Neptune's orbital distance without any risk of collision. The resonance ensures that whenever Pluto is closest to the Sun, Neptune is always far away on the other side of his orbit. They're locked in a perpetual gravitational dance, perfectly timed, so they never come close. Now, here's the question that changed our understanding of the outer solar system entirely. Why are there so many objects in resonances with Neptune? If the Kuiper Belt formed in place, with objects condensing from the protoplanetary disk exactly where we find them today, you wouldn't expect a large number of them to be sitting in perfect resonant orbits. Resonances are narrow. They occupy very specific orbital distances. The 3:2 resonance sits at about 39.5 astronomical units. The 2:1 resonance sits at about 47.5 astronomical units. These are thin bands. the chance of an object randomly forming at exactly the right distance to be in a resonance is small. You'd expect a few objects in resonance by coincidence, sure, but astronomers found hundreds of Plutinos in the 3-to-2 resonance alone, and they found significant populations in the 2-to-1, the 5-to-3, the 7-to-4, and several other resonances. This was far too many to be explained by chance. Something had actively pushed these objects into resonance. Something had taken objects that were originally on different orbits and herded them into these precise mathematical relationships with Neptune. And the answer, when scientists finally worked it out, was stunning. Neptune moved. Not a little. Not a slight orbital adjustment. Neptune migrated outward by billions of kilometers, slowly crawling away from the Sun over the course of hundreds of millions of years. And as it moved, it swept its resonances through the Kuiper Belt like a net through water, capturing objects and dragging them along. This idea that the giant planets didn't form in the orbits where we find them today is one of the most revolutionary concepts in modern planetary science. For most of the 20th century, scientists assumed the planets formed more or less where they are now. Jupiter formed at 5 astronomical units, Saturn formed at 9.5, Uranus at about 19, Neptune at 30. That was the standard picture, clean, simple, and as it turned out, almost certainly wrong. The first serious hint that something was off came from the Kuiper Belt itself. The overabundance of objects in Neptune's resonances was simply impossible to explain if Neptune had always been at 30 astronomical units. But if Neptune had started closer to the Sun, say around 20 to 25 astronomical units, and then migrated outward to its current position, everything suddenly made sense. As Neptune moved outward, the locations of its resonances moved outward too. The 3-to-2 resonance, which today sits at 39.5 astronomical units, would have been much closer to the Sun when Neptune was at 25 astronomical units. As Neptune crept outward, the resonance swept outward through the disk of icy bodies. Any object that the resonance encountered along the way could be captured, locked into the resonant orbit, and carried outward with Neptune. The resonance acted like a snowplow, pushing objects ahead of it as Neptune migrated. Let's think about how this capture process actually works for an individual object, because it's one of the most elegant mechanisms in planetary science. Picture a single icy body, maybe 50 kilometers across, orbiting peacefully at 35 astronomical units from the Sun. It's been on this quiet circular orbit for millions of years, slowly drifting around the Sun in the cold and dark. Meanwhile, Neptune is creeping outward. As Neptune moves, the location of its 3-to-2 resonance also shifts outward. At some point, the resonance reaches the exact distance where our icy body is orbiting. Now, something subtle but powerful begins to happen. The icy body starts to feel a periodic gravitational tug from Neptune that doesn't average out anymore. Each time Neptune completes 3 orbits, and the icy body completes 2, the 2 objects are in the same relative positions. The tug is always in the same direction. This repeated push begins to alter the icy body's orbit. If the capture is successful, the object's orbital period adjusts slightly, so that it stays locked in the 3-to-2 ratio as Neptune continues to move outward. The resonance acts like a gentle trap. The object doesn't suddenly jump to a new orbit. Instead, its orbit is slowly, continuously modified, always staying in step with Neptune's gradual migration. The object is carried outward, pushed to a greater and greater distance from the Sun, not by a violent kick, but by a sustained, rhythmic, gravitational nudge. Over hundreds of millions of years, this process can move an object by many astronomical units. An icy body that was born at 35 astronomical units might end up at 39.5, precisely where the 3:2 resonance sits today. It didn't form there. It was delivered there, gently and inexorably, by Neptune's migration. Not every object that encounters a sweeping resonance gets captured. The capture efficiency depends on how quickly Neptune is migrating. If Neptune moves too fast, the resonance sweeps past objects before the gravitational interaction has time to lock them in. They slip through the net. If Neptune moves more slowly, the interaction lasts longer and more objects are captured. The rate of Neptune's migration is therefore directly written into the number of objects we find in each resonance today. By counting Plutinos and objects in other resonances, astronomers can actually reconstruct how fast Neptune migrated. The data suggest Neptune's migration was relatively slow in its later phases, which allowed efficient capture and explains the large resonant populations we observe. But why would Neptune migrate in the first place? What force could push an entire planet outward by billions of kilometers? The answer lies in the interactions between the young giant planets and the massive disk of small icy bodies that surrounded them. In the early solar system, the region beyond the giant planets was filled with a dense disk of icy planetesimals. These were small bodies, typically a few kilometers to a few tens of kilometers across, left over from the planet formation process. The total mass of this disk was substantial, perhaps 35 to 50 Earth masses worth of material. As Neptune orbited the Sun, it occasionally had gravitational encounters with these small icy bodies. When Neptune passed close to a planetesimal, the encounter could go one of two ways. Neptune might fling the small body inward toward Jupiter and Saturn, or it might fling it outward toward the distant reaches of the solar system. Here's the critical part. When Neptune flung a planetesimal inward, Newton's third law demanded that Neptune itself received a tiny push outward. When Neptune flung a planetesimal outward, Neptune received a tiny push inward. You might think these effects would cancel out, but they didn't. Jupiter, sitting in the inner solar system with its overwhelming gravity, acted like a gravitational drain. Most of the planetesimals that Neptune flung inward were eventually captured or ejected from the solar system entirely by Jupiter. They didn't come back. But objects that Neptune flung outward often remained on orbits that brought them back for another encounter with Neptune. The net effect was that Neptune kept losing angular momentum in one direction, objects sent inward and removed by Jupiter, without gaining it back equally from the other direction. Over millions of years, this imbalance caused Neptune to slowly spiral outward. In 2005, a group of planetary scientists working at the observatory in Nice, France, published a landmark series of papers that modeled this migration in detail. Their model, which became known as the Nice model, proposed that all 4 giant planets migrated during the early solar system. Jupiter moved slightly inward, toward the Sun, while Saturn, Uranus, and Neptune all moved outward. The migration wasn't smooth and gentle. The Nice model proposed that at some point, Jupiter and Saturn crossed a mutual 2-to-1 resonance, meaning Saturn's orbital period became exactly twice Jupiter's. This crossing triggered a violent instability. The orbits of all 4 giant planets became chaotic. Uranus and Neptune were flung outward dramatically, plowing through the dense disk of icy planetesimals. The instability itself was brief by solar system standards, lasting perhaps only a few million years, but its effects were catastrophic. Think about what it means for a planet the mass of Neptune to be flung outward through a dense disk of small bodies. Neptune didn't gently drift through the disk, it was hurled into it. As it plowed through, it flung planetesimals in every direction. Some were hurled into the inner solar system, bombarding the terrestrial planets in what may correspond to a period of heavy bombardment, visible in the cratering records of the Moon and other rocky worlds. Others were flung outward to enormous distances, populating the Oort cloud, the vast spherical shell of icy bodies that surrounds the solar system at distances of thousands to tens of thousands of astronomical units. Some were ejected from the solar system entirely, becoming interstellar wanderers, icy bodies drifting through the galaxy unattached to any star. The Nice model has been refined considerably since 2005. Later versions suggested that Uranus and Neptune may have actually swapped positions during the instability, with Neptune starting closer to the Sun than Uranus and ending up farther. The timing of the instability has also been debated. The original Nice model placed it around 700 million years after the solar system formed, corresponding to a period of heavy bombardment about 3.8 billion years ago. More recent work suggests the instability may have happened earlier, perhaps within the first 100 million years. These details are still being debated, but the core idea that the giant planets migrated and that this migration reshaped the outer solar system is now widely accepted. Neptune's outward migration through the planetesimal disk was the single most transformative event in the history of the outer solar system. As Neptune plowed outward from roughly 20 to 25 astronomical units to its current position at 30, it completely rearranged everything in its path. Let's walk through what happened step by step. As Neptune moved outward, its resonances swept outward through the disk. Think of it like a series of invisible nets being dragged through water. The 3-to-2 resonance swept outward first, since it sits closer to Neptune. As it moved, it encountered icy bodies that were orbiting peacefully in the disk. Some of these bodies were captured by the resonance. Once captured, they were locked into the 3-to-2 orbital relationship with Neptune. As Neptune continued to move outward, these captured objects were carried along, pushed to greater and greater distances from the Sun. This is how the Plutinos were created. They weren't born at 39.5 astronomical units. They were born much closer to the Sun, and was swept outward by Neptune's migrating 3-to-2 resonance. Pluto itself was likely captured this way. It started closer to the Sun, was caught by the resonance, and was carried to its current orbit. The same process happened with other resonances. The 2-to-1 resonance, which today sits at about 47.5 astronomical units, also swept outward through the disk, capturing objects along the way. Objects trapped in the 2-to-1 resonance are sometimes called Plutinos. The 5-to-3, 7-to-4, and 5-to-2 resonances all capture their own populations of objects. Each resonance acts as a trap. Once an object falls into the resonance relationship, it's locked there, orbiting in precise synchronization with Neptune indefinitely. This explains why we see such large populations in these resonances. It's not coincidence, it's a direct result of Neptune's migration. Neptune's resonances acted as gravitational collectors, sweeping through the disk and gathering objects like a broom, pushing debris into distinct piles. But not every object was neatly captured into a resonance. In fact, most weren't. Many icy bodies encountered Neptune during its migration, and were simply scattered. A close gravitational encounter with Neptune could dramatically alter an object's orbit, kicking it onto a wildly elongated, highly inclined path. These scattered objects form what astronomers call the scattered disk. Scattered disk objects have orbits with very high eccentricities. Their closest approach to the Sun might be around 30 to 35 astronomical units, near Neptune's orbit, but their farthest point might be hundreds of astronomical units away. Their orbits are also often highly tilted relative to the plane of the solar system. Eris, the dwarf planet whose discovery helped trigger Pluto's reclassification, is a scattered disk object. Its orbit takes it from about 38 astronomical units at its closest to nearly 98 astronomical units at its farthest. That's an enormously elongated path. Eris wasn't born on this orbit. It was placed there by a gravitational encounter with Neptune, flung outward onto a stretched, tilted trajectory. The scattered disk is important because it tells us that objects do exist beyond the apparent edge of the classical Kuiper Belt. The belt may appear to end sharply at around 48 astronomical units, but that's only true for the well-behaved circular orbit population. Scattered disk objects, with their wild, eccentric orbits, extend far beyond that boundary. They're just harder to find because they spend most of their time at enormous distances from the Sun, where they're incredibly faint and slow-moving. They only become visible during the relatively brief portion of their orbit, when they're close enough to detect. Now, here's where Neptune's influence becomes truly nuanced. Not everything in the Kuiper Belt was scattered or captured. Remember the cold classical belt we discussed earlier? Those objects with calm, circular, low inclination orbits, sitting between roughly 42 and 47 astronomical units. This population appears to have largely survived Neptune's migration intact. And understanding why is crucial to understanding the belt's structure. When Neptune migrated outward, its gravitational influence was strongest in the regions closest to it. Objects near Neptune's new orbit were either captured into resonances, scattered onto chaotic orbits, or ejected from the solar system entirely. The inner part of the original disk was essentially destroyed. Any objects that had been orbiting between roughly 20 and 38 astronomical units were completely rearranged. Most were removed. Some were captured into resonances. A few were scattered to enormous distances. But objects farther out, beyond about 42 astronomical units, were in a kind of gravitational sweet spot. They were far enough from Neptune that its direct gravitational perturbations were weaker. The resonances that swept through this region did capture some objects, but many others were left untouched. Let's think about why this sweet spot exists, because it's not immediately obvious. You might expect that if Neptune's resonances swept through the entire disk, they'd capture or disturb everything, regardless of distance. But resonances don't work that way. A resonance is like a moving net, and the width of the net matters. Close to Neptune, the resonances are strong and wide. They can capture objects efficiently. But the farther a resonance is from Neptune, the narrower and weaker it becomes. At 42 astronomical units and beyond, the resonances that swept through were thin and relatively feeble. They could still capture some objects, which is why we see a resonant population even at those distances. But most objects in this region simply weren't close enough to the resonance center to be caught. The net passed through them without grabbing hold. Additionally, the gravitational perturbations from Neptune's direct influence, not through resonances, but through ordinary gravitational interaction, decrease with distance. An object at 44 astronomical units feels Neptune's gravity much more weakly than an object at 34 astronomical units. The perturbations are too weak to significantly alter its orbit over the age of the solar system. So objects beyond about 42 astronomical units experienced a milder version of Neptune's migration. They weren't untouched. Some were captured into distant resonances. Some had their orbits slightly excited. But the majority survived on roughly the same orbits they'd always had. These survivors are the cold classical Kuiper Belt. They're sitting approximately where they formed 4.5 billion years ago, on the same calm, circular orbits they've always had, carrying the same pristine icy composition they were born with. The cold classical belt is essentially a fossil, a preserved fragment of the original proto-planetary disk that existed before the giant planets migrated. It's one of the most ancient, least disturbed populations of objects in the entire solar system. Their physical properties confirm this. Remember those distinctly reddish surfaces and abundant binary pairs we discussed earlier? Those features only survive in an environment that has been gravitationally quiet for billions of years. If Neptune's migration had swept vigorously through this region, the binaries would have been torn apart and the population would show the same mixed, excited characteristics as the hot classical objects. The fact that the cold classicals retain their pristine properties tells us something important about Neptune's migration. It constrains how far Neptune traveled and how quickly it moved. If Neptune had migrated too far outward, past 42 or 43 astronomical units, it would have destroyed the cold classical belt entirely. The cold classicals would have been scattered or captured, and we wouldn't see them today on calm circular orbits. The very existence of this fossil population places a firm outer limit on Neptune's migration. Neptune stopped at 30 astronomical units because that's where the exchange of angular momentum with the planetesimal disk ran out of fuel. The disk was depleted and the migration stalled. The cold classical belt survived because Neptune's journey ended before reaching it. The hot classical population, by contrast, tells a very different story. These objects, with their excited, tilted, elliptical orbits, were almost certainly disturbed by Neptune's migration. Their physical differences from the cold classicals, the less uniform colors, the different size distribution, the scarcity of binary pairs, all point to a population that has been through a gravitational upheaval. Some of them may have originally formed much closer to the Sun, perhaps between 25 and 35 astronomical units, in the region that Neptune migrated through. As Neptune plowed outward, it flung these objects ahead of it, scattering them into the classical belt region on excited orbits. Others may have formed in place near the cold classicals, but had their orbits stirred up by the sweeping resonances or by close encounters with Neptune during the migration period. Either way, the hot population has been processed. It carries the scars of Neptune's passage. The hot and cold classical populations overlap in space, occupying the same general region of the belt between about 42 and 47 astronomical units. But they have completely different orbital characteristics, different histories and different origins, They coexist like two different communities living in the same neighborhood, but having arrived there by completely different routes. Let's also talk about what happened to the material that originally existed inside Neptune's current orbit. Before Neptune migrated, the region between roughly 20 and 30 astronomical units would have contained a dense disk of icy planetesimals. This material was almost entirely destroyed during the migration. As Neptune moved outward through this region, its gravity scattered, ejected, or captured virtually everything in its path. The belt was effectively erased in this zone. Today, the region between Uranus and Neptune is remarkably empty. There are almost no small bodies there. This emptiness itself is evidence of Neptune's migration. If Neptune had formed in place at 30 astronomical units, you'd expect some residual population of objects in the region just inside its orbit. The fact that this region is so clean tells us that something swept through it and removed everything. That something was Neptune. So let's put the full picture together. Neptune formed closer to the Sun than where it orbits today, probably somewhere around 20 to 25 astronomical units. The early outer solar system contained a massive disk of icy planetesimals extending well beyond the giant planets. Through gravitational interactions with this disk, and possibly triggered by a resonance crossing with Jupiter, Neptune began migrating outward. As it moved, its resonances swept through the disk, capturing objects into specific orbital relationships. Objects that weren't captured were scattered onto wild, eccentric orbits, creating the scattered disk. Objects in the region Neptune migrated through were largely destroyed or removed, but objects farther out, beyond about 42 astronomical units, were less affected. The cold classical belt survived as a fossil of the original disk. The hot classical population was stirred up, either by direct scattering from Neptune or by the passage of sweeping resonances. Neptune's fingerprints are all over the Kuiper Belt. The resonant populations, the Plutinos, the Teutinos, and all the other trapped groups couldn't exist without migration. The scattered disk, with its wild elongated orbits, was created by Neptune's gravitational encounters. The distinction between hot and cold classical populations reflects the boundary between regions that Neptune rearranged and regions it left mostly alone. Even the emptiness inside Neptune's orbit is a signature of its passage. The evidence is overwhelming. Neptune migrated, and that migration created most of the structure we observe in the Kuiper Belt today. But there's something Neptune's migration doesn't easily explain, and this is where our story takes its most puzzling turn. Neptune's migration can account for the resonant populations. It can explain the scattered disk. It can explain the difference between hot and cold classical objects. It can explain the empty region inside Neptune's orbit. But can it explain the cliff? Can it explain why the classical belt appears to end so sharply at around 48 astronomical units? If the protoplanetary disk extended well beyond this distance, and if the cold classical belt represents a surviving fragment of that disk, then why doesn't the cold classical population extend farther outward? Why does it stop? Neptune's 2-to-1 resonance sits at about 47.5 astronomical units. Some scientists have suggested that this resonance might mark the outer boundary of the classical belt, with Neptune's gravitational influence preventing stable orbits beyond it. But the math doesn't quite work out that neatly. The 2-to-1 resonance can destabilize orbits very close to it, but it shouldn't completely empty the region beyond. Objects at 50 or 55 or 60 astronomical units should still be able to exist on stable orbits. Neptune's gravity at those distances is weak. The resonances at those distances are thin and widely spaced. There's no obvious gravitational mechanism that would prevent a classical belt from extending much farther than 48 astronomical units. And yet, when astronomers look beyond that distance, the classical population essentially vanishes. Neptune shaped the Kuiper Belt profoundly. It captured objects into resonances, scattered others onto extreme orbits, stirred up the hot classical population, and left the cold classicals as a surviving fossil. It is without question the dominant sculptor of the outer solar system. But the sharp edge of the belt, the cliff, the sudden drop in the classical population beyond roughly 48 astronomical units, remains something that Neptune's migration alone struggles to fully explain. Something else may have set that boundary. Something that happened even before Neptune began its grand rearrangement, or something so subtle that we're only now beginning to understand it. That outer edge, that mysterious cliff where the belt appears to simply stop, is what we need to examine next. So we've established that Neptune reshaped the Kuiper Belt dramatically. Its outward migration swept objects into resonances, scattered others onto wild orbits, and divided the belt into distinct populations with different histories. Neptune's influence explains an enormous amount of the structure we observe. But now we arrive at the central puzzle, the thing that makes the outer solar system genuinely mysterious. The cliff. Astronomers first began to notice something strange in the early 2000s, as surveys of the outer solar system became more systematic and more thorough. The Kuiper Belt, as expected, contained a healthy population of objects between about 30 and 47 astronomical units. The resonant populations were there. The hot and cold classical populations were there. Everything looked roughly consistent with what models of Neptune's migration predicted. But when observers searched for objects beyond roughly 48 astronomical units, they found almost nothing. Not a gradual thinning out. Not a slow decline. A sharp, sudden drop. The population of objects on stable, low eccentricity, low inclination orbits, the type of objects that define the classical belt, essentially disappeared beyond this distance. The surveys kept looking. The telescopes were powerful enough to detect objects at these distances, at least the larger ones. The search techniques were well established, and yet, the objects simply weren't there. Now, let's be precise about what astronomers are actually measuring when they say the belt ends, because this is more subtle than it might seem. Astronomers don't directly count every object in the Kuiper Belt. They can't. Most Kuiper Belt objects are far too small and faint to see with any existing telescope. What astronomers do instead is survey specific patches of sky very carefully, cataloguing every object they find, measuring its brightness, its position, and its motion. From these detections, they build a statistical picture. They estimate how many objects must exist at a given distance based on how many they actually detected, adjusted for how difficult objects at that distance are to find. This adjustment is critical, and it's called a survey's completeness correction. Here's why it matters. Imagine you're trying to count birds in a forest. Near the edge of the forest, where it's open and well lit, you can see most of the birds. Your count is fairly accurate. But deeper in the forest, where it's dark and the trees are thick, you can only see a fraction of the birds that are actually there. You know you're missing some, so you apply a correction. Based on how many birds you spotted in the region you could see well, you estimate how many must exist in the regions you couldn't see well. Astronomers do the same thing with the Kuiper Belt. Objects at 35 astronomical units are relatively bright because they're relatively close and receive more sunlight. Surveys can detect these objects fairly completely, meaning they find a large fraction of the objects that actually exist at that distance. But objects at 50 astronomical units are much fainter. They're farther from the sun, so they receive less sunlight to reflect. They're also farther from Earth, so whatever light they do reflect has to travel a greater distance to reach our telescopes. The combination of these two effects means that an object at 50 astronomical units appears far dimmer than an identical object at 35 astronomical units. Specifically, the brightness of a solar system object drops roughly with the fourth power of its distance from the sun. This is a devastating effect. If you double an object's distance from the sun, its apparent brightness doesn't just halve, it drops by a factor of 16. An object at 50 astronomical units appears roughly 4 times fainter than an identical object at 35 astronomical units. 4 times fainter is enormous in observational astronomy. It means that surveys that can detect all objects larger than, say, 100 kilometers at 35 astronomical units might only be able to detect objects larger than several hundred kilometers at 50 astronomical units. Smaller objects at that greater distance would simply be invisible. This is where the question of observational bias comes in. And it's a legitimate question that astronomers have spent decades grappling with. When we see the population of classical Kuiper Belt objects drop sharply beyond 48 astronomical units, is the drop real? Or are we simply failing to detect objects that are actually there because they're too faint? This question was taken very seriously from the beginning. Astronomers are well aware of observational biases, and they've designed surveys specifically to account for them. One of the most important of these was the OSSOS project, the Outer Solar System Origin Survey, which ran from 2013 to 2017 using the Canada-France-Hawaii telescope. OSSOS was deliberately designed to have extremely well-characterized detection limits. The researchers knew exactly how faint an object they could detect at every point in their survey field. They knew precisely how far away an object could be and still be visible. This allowed them to calculate completeness corrections with high confidence. When OSSOS analyzed the distribution of Kuiper Belt objects, the result was clear. The drop beyond 48 astronomical units is real. It's not an artifact of observational bias. Even after applying generous corrections for the difficulty of detecting faint, distant objects, the classical population genuinely declines sharply. The belt doesn't just appear to end, it actually does end, at least in terms of the classical, dynamically cold population. Other surveys have reached the same conclusion. The Deep Ecliptic Survey, the Canada-France Ecliptic Plane Survey, and multiple follow-up studies have all confirmed that the outer edge of the classical belt is a real physical feature, not an observational illusion. But let's be extremely careful here about what we mean by end. Because one of the biggest misconceptions about the Kuiper Cliff is that nothing exists beyond it. That's absolutely wrong. The cliff refers specifically to the sharp decline in the classical belt population, the objects on calm, nearly circular low inclination orbits. Beyond about 48 astronomical units, this population effectively vanishes. But other populations of objects absolutely do exist at much greater distances. The outer solar system beyond the cliff is not empty. It's just populated by different kinds of objects with very different orbital characteristics. The scattered disk, which we discussed in the context of Neptune's migration, extends far beyond the classical belt. Scattered disk objects have highly elliptical orbits that can carry them to enormous distances. Ares, whose stretched orbit we encountered earlier, is a prime example. These objects have perihelion distances, the point in their orbit where they come closest to the Sun, that are relatively near Neptune. This means they still interact gravitationally with Neptune, at least weakly. Their orbits are not stable in the long-term sense that classical belt orbits are. Over billions of years, further encounters with Neptune can continue to modify their paths. Some will eventually be ejected from the solar system entirely. Others will have their orbits pumped up to even greater eccentricities, sending them farther and farther out. Then there are the detached objects. These are some of the most intriguing bodies in the entire solar system. Detached objects have orbits that take them far beyond Neptune, similar to scattered disk objects, but with one critical difference. Their perihelion distances are so large that they never come close enough to Neptune for the planet's gravity to significantly affect them. They're gravitationally detached from Neptune. They orbit in isolation, untouched by any known planet, following paths that no currently understood mechanism can easily explain. The most famous detached object is Sedna. Discovered in 2003 by astronomers Mike Brown, Chad Trujillo, and David Rabinowitz, Sedna stunned the scientific community. Its orbit is extraordinary. At its closest approach to the Sun, Sedna comes no nearer than about 76 astronomical units. That's already well beyond Neptune and well beyond the classical Kuiper Belt. But at its farthest point, Sedna retreats to roughly 937 astronomical units from the Sun. Its orbital period is about 11,400 years. The last time Sedna was at its closest point to the Sun, human civilization was in the early stages of the Neolithic period. People were just beginning to develop agriculture. Sedna's orbit is deeply puzzling. No known planet can account for it. Neptune is too far away to have placed Sedna on this path. Jupiter, Saturn, and Uranus are even farther from relevance. Sedna's perihelion is so distant that it's essentially immune to gravitational perturbations from any of the giant planets. Something else put Sedna on this orbit. But what? We'll explore the possible answers shortly. For now, the important point is that Sedna exists well beyond the classical Kuiper Belt's edge. It's proof that the outer solar system is not empty beyond the cliff. Objects are out there. They're just rare, far-flung, and on very different kinds of orbits than the classical belt population. Another important detached object is 2012 VP113, informally nicknamed Biden after the then vice president because of its VP designation. Discovered in 2014 by astronomers Chad Trujillo and Scott Shepard, this object has a perihelion distance of about 80 astronomical units, even more detached from Neptune's influence than Sedna. Its orbit carries it out to roughly 450 astronomical units. Like Sedna, its orbit cannot be explained by the gravitational influence of any known planet. These detached objects are significant because they tell us something profound. The outer solar system has been sculpted by forces beyond just Neptune. Whatever placed Sedna and 2012 VP113 on their extreme orbits must have been powerful and must have operated long ago. because these orbits are stable over billions of years. These objects aren't being actively moved around. They were placed on these paths in the distant past and have been following them ever since. Beyond the scattered disk and the detached objects, there are also the extreme trans-Neptunian objects. These are bodies with very large semi-major axes, meaning the average radius of their orbit is very large, typically beyond 150 astronomical units. These objects spend most of their time at enormous distances from the Sun, moving incredibly slowly through the darkness. They're extraordinarily difficult to detect because they're usually far from the Sun and very faint. We only spot them during the brief portion of their orbit, when they're relatively close to us, near their perihelion. The rest of the time, they're invisible to our telescopes. This means the handful of extreme trans-Neptunian objects we've found almost certainly represent a much larger population that remains hidden. Now, here's the key takeaway from all of this. The Kuiper Cliff, the sharp drop in the classical belt population beyond about 48 astronomical units, is real. It has been confirmed by multiple independent surveys with careful completeness corrections. It is not an artifact of observational bias, but the cliff does not mean that nothing exists beyond it. Scattered disk objects extend to hundreds of astronomical units. Detached objects like Sedna orbit at distances approaching 1,000 astronomical units. Extreme trans-Neptunian objects trace paths even farther out. The outer solar system is populated far beyond the cliff, just not by the kind of objects that define the classical Kuiper Belt. The cliff is an edge in a specific population, not an edge of the solar system itself. This distinction is crucial for understanding what the cliff actually tells us. The classical Kuiper Belt consists of objects on nearly circular, low inclination orbits. These are the most dynamically pristine objects in the outer solar system. Their calm orbits suggest they formed in place and have remained relatively undisturbed. The fact that this specific population ends sharply at about 48 astronomical units tells us something about the conditions under which these objects formed, or about the processes that later removed them. This scattered disk and detached objects, by contrast, are on highly disturbed orbits. They've been moved around by gravitational encounters. Their current positions don't necessarily reflect where they formed. So the existence of scattered and detached objects beyond the cliff doesn't contradict the cliff's reality. These populations were placed on their current orbits by dynamical processes, not born there. Let's also address the observational challenges more directly, because even though the cliff is real, our picture of the outer solar system is still profoundly incomplete, and that incompleteness affects how confidently we can interpret what we see. The fundamental problem is brightness, or rather, the lack of it. Objects in the outer solar system shine only by reflected sunlight. They have no internal source of light. The amount of sunlight hitting an object decreases with the square of its distance from the sun. The amount of reflected light reaching Earth then decreases with the square of the object's distance from Earth. For distant Kuiper Belt objects, both of these distances are large, so the combined effect is devastating. A Kuiper Belt object at 50 astronomical units receives only about 1/3 the sunlight that a similar object at Neptune's orbit would receive. That might not sound devastating on its own, but the reflected light from the object also has to travel a greater distance back to Earth, dimming further along the way. The combined effect means that even large objects become extraordinarily faint at great distances. Consider a Kuiper Belt object 100 kilometers in diameter with a typical surface reflectivity, what astronomers call albedo, of about 10%. At 40 astronomical units, this object would have an apparent magnitude of roughly 27. That's extremely faint, near the detection limit of the largest ground-based telescopes. At 60 astronomical units, the same object would be about 2 magnitudes fainter, roughly magnitude 29. At 80 astronomical units, it would be fainter still. Each magnitude represents a factor of about 2.5 in brightness, so a 2 magnitude difference means the object is about 6 times fainter. The practical consequence is stark. A survey that can detect every object larger than 100 kilometers at 40 astronomical units might miss identical objects at 60 astronomical units entirely. They'd be too faint to register on the detector. Only objects that are much larger, several hundred kilometers or more, would be visible at these greater distances. This means our census of the outer solar system is heavily biased toward the nearer, brighter objects. We have a reasonably good inventory of large Kuiper Belt objects within the classical belt's boundaries. But beyond about 50 astronomical units, our inventory is sparse, limited to only the very largest and most reflective objects. There could be hundreds or thousands of small bodies out there that we simply cannot see with current technology. This doesn't contradict the reality of the cliff. The surveys that established the cliff accounted for these detection limits. They corrected for the fact that distant objects are harder to find. Even after these corrections, the population decline is real. But it does mean that our picture of what exists beyond the cliff is incomplete. There might be a thin, sparse population of small classical type objects beyond 48 astronomical units that current surveys aren't sensitive enough to detect. These wouldn't change the basic picture. The cliff would still be a dramatic population decline, but they could modify the details of how sharp the edge truly is. This is one of the reasons why future surveys are so eagerly anticipated. The Vera Rubin Observatory in Chile, which will conduct the Legacy Survey of Space and Time, a 10-year campaign to repeatedly image the entire visible southern sky, is expected to discover tens of thousands of new Kuiper Belt objects, vastly expanding our catalogue of the outer solar system. Among these discoveries, there will almost certainly be objects beyond the current classical belt boundary. The Vera Rubin Observatory won't just find more of what we already know about. It will probe deeper into the outer solar system than any previous survey, potentially revealing populations of objects we don't yet know exist. If there's a thin, sparse extension of the classical belt beyond 48 astronomical units, the Vera Rubin Observatory has the best chance of finding it. Now, there is one more topic we need to address before we move on to the possible explanations for the cliff, and it's a topic that generates enormous public interest, often more interest than the underlying science warrants. Planet 9. In 2016, astronomers Konstantin Batygin and Mike Brown at the California Institute of Technology published a paper that reignited one of the oldest questions in astronomy. Is there an undiscovered planet hiding in the outer solar system? Their argument was based on a curious observation. Several of the most distant trans-Neptunian objects, those with extremely large orbits and perihelion distances beyond Neptune's influence, appeared to have orbits that were clustered together in space. Specifically, the long axes of their orbits. The direction in which their orbits are most elongated seem to point in roughly the same direction. If these orbits were randomly distributed, you wouldn't expect this kind of clustering. The odds of it happening by chance, Batygin and Brown argued, were very small. They proposed that the most natural explanation was the gravitational influence of an unseen planet. A planet roughly 5 to 10 times the mass of Earth, orbiting far beyond the Kuiper Belt at a distance of perhaps 400 to 800 astronomical units from the Sun. This hypothetical world became known as Planet 9. The Planet 9 hypothesis generated enormous excitement, both within the scientific community and among the general public. The idea of an undiscovered planet in our own solar system is inherently thrilling, and the mathematical analysis behind the proposal was serious and rigorous. Batygin and Brown are respected planetary scientists. Their argument was not speculation. It was based on careful statistical analysis and dynamical modeling. But here's what's crucial to understand. The Planet 9 hypothesis remains unconfirmed. No direct observation of Planet 9 has been made. Nobody has seen it through a telescope. Nobody has detected its infrared glow. Despite extensive searches, including dedicated surveys using some of the largest telescopes in the world, Planet 9 has not been found. This doesn't necessarily mean it doesn't exist. If Planet 9 is at the far end of its proposed orbit, several hundred astronomical units from the Sun, it would be extraordinarily faint. Even a planet several times the mass of Earth would reflect very little sunlight at that distance, and because its proposed orbit is so large, it would move incredibly slowly against the background stars. Finding it would require searching a vast area of sky for an extremely faint, slowly moving point of light. It would be like searching for a specific grain of sand on a beach at night with a penlight. So the failure to find Planet 9 so far doesn't disprove the hypothesis. The search is genuinely difficult, and the sky is very large. However, the statistical evidence for Planet 9 has also come under scrutiny. Several independent studies have questioned whether the observed clustering of distant trans-Neptunian object orbits is as significant as originally claimed. The concern is observational bias. Surveys for distant objects don't cover the whole sky evenly. They tend to focus on certain regions, at certain times of year, under certain conditions. This means we're more likely to discover objects in some parts of the sky than others. If we're preferentially finding objects whose orbits happen to be oriented in a particular direction, simply because that's where we're looking most intensively, then the apparent clustering might be an artifact of how we search rather than a real physical effect. Several studies, including analyses by the OSSOS team, have argued that when observational biases are carefully accounted for, the clustering signal weakens considerably and may not be statistically significant. Other studies have found that the clustering does appear real, even after bias corrections. The debate is ongoing. As of now, there is no scientific consensus on whether the orbital clustering of extreme trans-Neptunian objects requires a Planet 9 to explain it. And here's the point that matters most for our story. Planet 9, even if it exists, is not required to explain the Kuiper Cliff. The sharp outer edge of the classical Kuiper Belt was recognized before the Planet 9 hypothesis was proposed. And the leading explanations for the cliff, which we'll explore shortly, don't depend on Planet 9 at all. The cliff exists at about 48 astronomical units. Planet 9, if it exists, orbits at several hundred astronomical units. The two phenomena operate at very different distances, and likely have different causes. Could Planet 9 influence the outer Kuiper Belt? potentially. A massive planet orbiting at hundreds of astronomical units would have long-range gravitational effects that could sculpt the distribution of distant objects. It could explain the orbits of detached objects like Sedna and 2012 VP113, objects whose extreme orbits are otherwise difficult to account for. But the cliff itself, the sharp decline in the classical population at 48 astronomical units, is much too close to be primarily caused by a planet orbiting several hundred astronomical units away. The cliff and Planet 9, if Planet 9 is real, are likely separate phenomena with separate explanations. It's also worth noting that there are other proposed explanations for the clustered orbits of extreme trans-Neptunian objects that don't require Planet 9 at all. Some scientists have suggested that the clustering could result from the combined gravitational effects of many small objects in the distant solar system rather than one large planet. Others have proposed that a passing star in the Sun's early history could have sculpted these orbits. Still, others have argued that the clustering might simply be a statistical illusion that will disappear as more objects are discovered and our survey coverage becomes more uniform. The Planet 9 question is genuinely open. It might exist, it might not. Future surveys, particularly the Vera Rubin Observatory, will discover many more extreme trans-Neptunian objects, dramatically improving the statistical evidence one way or the other. If Planet 9 does exist, the Vera Rubin Observatory might even find it directly, depending on where it is in its orbit and how bright it is. If it doesn't exist, the expanded catalogue of distant objects should eventually make that clear as well. For now, the honest scientific answer is that we don't know whether Planet 9 is real. What we do know is that the Kuiper Cliff doesn't need Planet 9 to be explained. The cliff is a feature of the classical belt at 48 astronomical units. Its cause lies in the formation and early evolution of the solar system, in the physics of how icy bodies grow in a thin protoplanetary disk, in the ways Neptune's migration rearranged the outer solar system, and possibly in events that happen before any of the planets reach their current orbits. These are the explanations we need to examine, not a hypothetical planet hundreds of astronomical units away, but the deep history of the solar system's birth and early childhood. That history is written in the orbits and populations of the Kuiper Belt, and the cliff, that sharp, abrupt decline where the classical belt simply seems to stop, is the most dramatic sentence in the entire story. So we've arrived at the deepest question. We know the Kuiper Cliff is real. We know the classical belt's population drops sharply beyond about 48 astronomical units. We know that Neptune's migration sculpted much of the belt's internal structure. We know that objects do exist beyond the cliff, but they're scattered disk bodies and detached objects on wild, eccentric orbits, not the calm, circular classical population. The question now is straightforward, but enormously difficult to answer. What caused the edge? What carved this boundary into the outer solar system? Why does the classical belt stop where it does? There is no single, universally accepted answer. Instead, there are several competing explanations, each with its own strengths and weaknesses. Some of these explanations could work alone, others might work in combination. And the honest truth is that after decades of study, the scientific community has not yet reached a consensus. The Kuiper Cliff remains one of the outstanding unsolved problems in planetary science. But the proposed explanations are fascinating, and understanding them takes us deep into the physics of how solar systems form, how they evolve, and how they preserve the scars of their violent early histories. The first and perhaps most fundamental explanation is that the belt ends where the protoplanetary disk itself ran out of usable material. Remember, the Kuiper Belt formed from the leftovers of the protoplanetary disk, the vast cloud of gas and dust that surrounded the young sun. The disk wasn't uniform. It had structure. Close to the sun, the disk was dense and hot. Farther out, it was thinner and colder. The density of solid material in the disk decreased with distance from the sun, roughly following a power law. This means that the farther from the sun you go, the less material was available to build things. In the inner solar system, where the disk was dense, planetesimals could grow quickly. Collisions between small bodies were frequent because there were many of them in a relatively small volume. Growth through accretion, the process of small bodies sticking together to form larger ones, was efficient. Rocky planets formed within the first 10 to 100 million years. Farther out, beyond the frost line, the addition of ices increased the amount of solid material available, allowing the giant planet cores to grow. But even with the ice bonus, the farther you went from the sun, the thinner the disk became. And out beyond about 40 to 50 astronomical units, the disk was genuinely sparse. Here's the problem. Building anything large in a thin, spread out disk takes an extraordinarily long time. The rate at which bodies grow through accretion depends on how often they collide. And how often they collide depends on how densely packed they are. In a dense environment, collisions are frequent and growth is fast. In a sparse environment, collisions are rare and growth is painfully slow. The growth timescale depends not just on density but also on orbital speed, and objects farther from the sun orbit more slowly. At Earth distance, an object completes one orbit per year, giving it many chances to encounter other material on each pass. At 40 astronomical units, a single orbit takes about 250 years. At 50 astronomical units, it takes roughly 350 years. At 60, nearly 470 years. Each orbit is an opportunity for the growing body to sweep through its feeding zone and accumulate more material. Fewer orbits per unit time means slower growth. The combination of lower density and slower orbital speed is devastating. At 40 astronomical units, growth was already sluggish. Bodies could build up to sizes of a few hundred kilometers over the age of the solar system, but only barely. At 50 or 60 astronomical units, the disk was thinner still. The time needed for bodies to grow to even modest sizes exceeded the age of the solar system itself. Bodies simply didn't have enough time to grow. They got stuck at small sizes, perhaps just a few kilometers across. Models suggest that at 50 astronomical units, building a body even 100 kilometers across could take longer than 10 billion years. That's more than twice the current age of the solar system. The material was there in principle, but the clock ran out before anything substantial could be assembled. And here's the critical consequence. Very small bodies are extremely vulnerable to destructive processes. They can be ground down by collisions with other small bodies. They can be blown outward by radiation pressure from the young sun. They can be dispersed by gravitational perturbations from passing objects. A population of objects that never grew large enough to be gravitationally stable might have been gradually eroded away over billions of years, leaving the region beyond the classical belt effectively empty. This explanation is appealing because it doesn't require any special event or unusual circumstance. It's just physics. The protoplanetary disk had a density profile that decreased with distance. Beyond a certain distance, the density was too low for significant growth to occur. The belt ends where the disk became too thin to build anything durable. The cliff isn't an edge that was carved by some external force. It's a growth limit, a boundary beyond which the solar system's construction process simply couldn't complete its work. But there's a complication. If the disk just gradually thinned out, you would expect the population to gradually decline, not drop off sharply. A smooth density profile should produce a smooth population decline. The Kuiper Cliff, however, appears to be abrupt. The population doesn't slowly fade over tens of astronomical units. It drops dramatically over a relatively narrow range of distances. A simple model of declining disk density, while it can explain why the belt eventually ends, has difficulty explaining why it ends so suddenly. This leads to the second explanation, which is sometimes called collisional grinding. The idea here is that the classical belt might have originally extended beyond 48 astronomical units, but the objects out there were ground down to dust over billions of years through mutual collisions. In the inner classical belt, objects grew large enough to survive collisions. A body several hundred kilometers across can absorb impacts from smaller objects without being destroyed. It might lose some material, but it survives as a coherent body. But in the outer reaches of the belt, where growth was slower, most objects might have remained small, and small objects are vulnerable. When two small bodies collide at typical Kuiper Belt velocities, a few hundred meters per second to perhaps a kilometer per second, the collision can be destructive rather than constructive. Instead of sticking together and growing, the bodies shatter into fragments. Those fragments then collide with other fragments, producing even smaller pieces. Over billions of years, this cascading destruction could grind the original population down to microscopic dust. And microscopic dust doesn't stay in the Kuiper Belt. It's affected by solar radiation pressure and by a drag effect called the Poynting-Robertson effect, which causes small particles to slowly spiral inward toward the sun. Over time, the dust is removed from the outer belt entirely. Collisional grinding could explain why the outer classical belt appears empty. The objects might have been there once, but they've been destroyed. The belt didn't form with a sharp edge. It acquired one over time as the outer population was slowly abraded away. This explanation has some genuine observational support, and it comes from an unexpected place: other star systems. Over the past 2 decades, infrared telescopes have detected debris disks around dozens of nearby stars. These are rings of dust and small particles orbiting other stars, produced by ongoing collisions between small bodies in their own equivalents of the Kuiper Belt. The star Fomalhaut, about 25 light-years from Earth, has a narrow, well-defined debris ring with sharp edges that look strikingly similar to what we'd expect the Kuiper Belt to look like from the outside. Beta Pictoris has an even more prominent debris disk that has been studied extensively. AU Microscopii, a young red dwarf star, has a debris disk that shows evidence of active collisional processing with fast-moving features that may be clouds of ground-up material being blown outward by stellar radiation. These debris disks show us that collisional grinding is a real, active process operating in planetary systems across the galaxy. The dust we see in these systems is being continuously produced by collisions between larger bodies and continuously removed by radiation pressure and other forces. If it happens around other stars, it almost certainly happened and continues to happen in our own solar system. However, collisional grinding also has difficulties explaining the sharpness of the cliff. The grinding rate depends on the density of objects and their collision velocities. In the outer belt, where objects are more spread out, collisions are less frequent. You might expect grinding to be slower out there, not faster. So why would the outer belt be ground down more than the inner belt? One possibility is that the objects in the outer belt were smaller to begin with, because growth was slower out there. Smaller objects are easier to destroy. So even though collisions were less frequent, each collision was more likely to be destructive because the targets were smaller and more fragile. There's a critical size threshold at work here. Below a certain size, roughly 10 to 50 kilometers depending on the material's strength and composition, a body can be completely shattered by a collision with something much smaller than itself. Above the threshold, the body's self-gravity is strong enough to pull most of the fragments back together after an impact. It might be battered and cracked, but it reassembles itself into a rubble pile and survives. This creates a sharp dividing line between populations that endure and populations that don't. If the inner belt produced objects above this survival threshold, while the outer belt never did, collisional grinding would preferentially destroy the outer population while leaving the inner population intact. The cliff would then represent the boundary between survival and destruction. The third explanation is perhaps the most dramatic. It proposes that the outer edge of the protoplanetary disk was truncated not by internal processes, but by an external event. A close encounter with a passing star. Our sun did not form in isolation. Stars almost never do. The sun formed in a stellar nursery, a dense cloud of gas and dust where hundreds or thousands of stars were being born simultaneously. These birth clusters are common in the galaxy. We can see them around us today. The Orion Nebula contains a young cluster of several thousand stars, packed into a region just a few light years across. The Pleiades is another cluster, older and more spread out, but still recognizable as a family of stars born from the same cloud. The sun's birth cluster would have looked something like these. Hundreds, or perhaps thousands of young stars, many still surrounded by their protoplanetary disks, all orbiting their common center of mass in a relatively small volume of space. In such an environment, stars were packed much closer together than they are today. In a typical birth cluster, stars might be separated by only a few thousand astronomical units, compared to the roughly 270,000 astronomical units that separate the Sun from its nearest current neighbor, Proxima Centauri. Clusters like this don't last forever. Over tens of millions of years, the stars gradually drift apart, dispersed by their mutual gravitational interactions and by the evaporation of the gas that held them together. Eventually, the cluster dissolves, and the stars spread out into the general galactic population. The Sun's birth siblings are now scattered across the Milky Way, unrecognizable among the hundreds of billions of other stars. But during the brief period when the Sun was still in its birth cluster, close encounters between stars were not rare. A young star passing within a few hundred astronomical units of our Sun would have been a plausible event, perhaps even likely. And such a close passage would have had a devastating effect on the outer protoplanetary disk. When a star passes close to another star that has a disk of material around it, the passing star's gravity pulls on the outer portions of the disk. Material that is loosely bound, far from the central star, and therefore weakly held by its gravity, can be stripped away entirely. The outer edge of the disk is literally torn off. The result is a disk with a sharp outer boundary, truncated at whatever distance corresponds to the point where the passing star's gravity overcame the central star's grip on the disk material. The truncation radius depends on how close the encounter was and how massive the passing star was. A rough rule of thumb from simulations is that the disk gets truncated to about 1/3 to 1/2 of the closest approach distance. So a star passing at 150 astronomical units would truncate the disk to about 50 to 75 astronomical units. A passage at 100 astronomical units would cut the disk even shorter. The physics of disk truncation by a stellar flyby has been studied extensively through computer simulations. These simulations show that a moderately close stellar encounter, a star passing within roughly 100 to 200 astronomical units of the Sun, could truncate the protoplanetary disk at about 45 to 50 astronomical units. This distance is remarkably close to the observed location of the Kuiper Cliff. The simulations also show that the truncation can be quite sharp. The disk doesn't slowly taper off near the truncation radius. It drops abruptly because the passing star's gravity acts as a knife edge, removing everything beyond a certain distance while leaving the inner disk relatively untouched. This explanation is attractive for several reasons. It naturally produces a sharp edge, which is the defining feature of the Kuiper Cliff. It places the edge at roughly the right distance, and it's astrophysically plausible. The Sun almost certainly formed in a cluster where close stellar encounters would have occurred. The timing works too. This encounter would have happened very early, within the first few 100 million years of the solar system's existence, while the Sun was still in its birth cluster. After the cluster dispersed and the stars drifted apart, no further encounters would have occurred. The truncation would have been a one-time event, setting the outer boundary of the disk before the giant planets finished forming and migrating. The stellar flyby hypothesis also has a potential connection to the detached objects like Sedna. Remember, Sedna's orbit, with its enormous distance from the Sun and its large perihelion, cannot be explained by any known planet, but a passing star could do it. As a star passed close to the young solar system, it could have not only truncated the outer disk, but also gravitationally lifted some objects from the outer disk onto the extreme detached orbits we see today. Simulations have shown that a single stellar flyby can simultaneously explain the Kuiper Cliff, the truncation of the classical belt, and the orbits of detached objects like Sedna and 2012 VP113. One event, one encounter, potentially explaining multiple mysteries. But the stellar flyby hypothesis is not without its problems. The main difficulty is that we can't directly observe the event. It would have happened over 4 billion years ago. We can't rewind the clock and watch it happen. We can model it in simulations, and the simulations look promising, but simulations can be tuned. The outcome depends on the mass of the passing star, how close it came, how fast it was moving, the angle of its approach relative to the disk, and the timing relative to the planet formation process. Different assumptions produce different results. And while many plausible flyby scenarios can produce a cliff at roughly the right distance, the exact details are uncertain. There's also the question of uniqueness. The same stellar flyby that could explain the Kuiper Cliff could also have disrupted the inner solar system in ways that might not be consistent with what we observe. A star passing close enough to truncate the disk at 50 astronomical units would also have perturbed Neptune's orbit, and possibly the orbits of other planets. The flyby would need to have happened at just the right time, before the planets reached their final positions, but after enough material had accumulated to eventually build them. The timing constraints are tight, so where does this leave us? We have 3 main explanations for the Kuiper Cliff. The formation limit hypothesis says the disk was too thin, beyond about 48 astronomical units, for objects to grow to durable sizes. The collisional grinding hypothesis says objects did form out there but were ground to dust over billions of years. The stellar flyby hypothesis says the outer disk was ripped away by a passing star early in the solar system's history. Each explanation has strengths, each has weaknesses, and the most likely answer might be a combination. The disk probably did thin out with distance, making growth slower and more difficult in the outer regions. Collisional grinding probably did erode smaller objects over time, and a stellar flyby might have set the outer boundary by truncating the disk entirely. All three processes could have contributed, reinforcing each other to produce the sharp edge we observe today. There's also a possible role for Neptune, even beyond what we discussed earlier. Neptune's 2-to-1 resonance sits at about 47.5 astronomical units, very close to the observed edge of the classical belt. While this resonance alone probably can't explain the cliff, it might have helped sharpen it. Here's how. Objects orbiting near the 2-to-1 resonance are subject to periodic gravitational kicks from Neptune. These kicks can pump up an object's eccentricity, stretching its orbit from a near circle into an elongated ellipse. Once the eccentricity gets high enough, the object's closest approach to the Sun drops into Neptune's orbital zone. At that point, Neptune can scatter or eject the object entirely. This process doesn't happen instantly. It plays out over hundreds of millions of years, but it's relentless. Over the age of the solar system, the 2-to-1 resonance has systematically cleared out objects near its location, creating a gap in the population. This gap coincides almost perfectly with the observed edge of the classical belt. The resonance didn't create the cliff from scratch, but it may have taken a boundary that already existed, whether from disk thinning, collisional erosion, or stellar truncation, and sharpened it further by selectively removing objects near the edge. Think of it as Neptune adding a final polish to an edge that was already rough cut by some earlier process. This brings us to the future, because the Kuiper Cliff, while well established observationally, is still understood through an incomplete dataset. We've discovered about 2,000 Kuiper Belt objects so far. That sounds like a lot, but it's a tiny fraction of the total population. Estimates suggest there could be hundreds of thousands of objects larger than 100 kilometers in the Kuiper Belt. We found barely 1% of them. And beyond the classical belt, our census is even more sparse. We've discovered a handful of detached and extreme trans-Neptunian objects, maybe a few dozen at most. These almost certainly represent a much larger population that remains hidden in the darkness. The Vera Rubin Observatory is going to change everything. Its legacy survey of space and time will systematically scan the southern sky for a full decade, with a sensitivity and cadence far beyond any previous effort. Its 8.4 meter mirror and 3.2 gigapixel camera are expected to reveal between 40,000 and 100,000 new Kuiper Belt objects. That's not a modest improvement. That's a revolution. It's the difference between looking at the Kuiper Belt through a keyhole and throwing open a door. With tens of thousands of new objects, astronomers will be able to map the belt structure in exquisite detail. They'll determine the exact shape of the population decline at the outer edge. Is it a sharp step function, dropping from a healthy population to zero over just a few astronomical units? Or is it more gradual than current data suggest, with a thin tail of objects extending beyond 48 astronomical units that existing surveys simply couldn't detect? The answer will tell us which explanation for the cliff is most likely. A very sharp edge would favour the stellar flyby hypothesis, because truncation by a passing star naturally produces a clean cut. A more gradual decline would favour the formation limit hypothesis, where the disk slowly thinned out and objects became smaller and more fragile at greater distances. The Vera Rubin Observatory will also discover many more scattered disk and detached objects. These distant bodies are crucial for testing the Planet 9 hypothesis and for understanding the dynamical history of the outer solar system. If the orbital clustering of extreme trans-Neptunian objects is real, a much larger sample will make the clustering signal unmistakable. If it's an observational artifact, a larger sample with better sky coverage will wash it out. Either way, we'll have an answer, or at least a much better informed debate. Other telescopes and missions will contribute as well. The Subaru telescope in Hawaii has already been instrumental in discovering distant trans-Neptunian objects, and ongoing surveys with this telescope continue to push deeper into the outer solar system. Space-based infrared observatories can detect the faint thermal emission from distant objects, complementing the reflected light surveys from the ground. And proposed missions to the outer solar system, including concepts for spacecraft that would fly through the Kuiper Belt and study its objects up close, will provide detailed information about the composition, size distribution, and surface properties of these ancient worlds. The New Horizons spacecraft, which flew past Pluto in 2015 and then flew past the Kuiper Belt object Arrokoth in 2019, demonstrated what close-up exploration of the Kuiper Belt can reveal. Arrokoth, a small contact binary made of two lobes that gently merged billions of years ago, showed us what a pristine, undisturbed Kuiper Belt object looks like. Its surface was remarkably uniform, covered in reddish organic material. Its shape suggested it formed through a gentle, slow-speed collision, consistent with the calm, low-velocity environment of the cold classical belt. Every object we study up close teaches us something new about the conditions in the outer protoplanetary disk and the processes that shape the belt. Future missions to other Kuiper Belt objects would expand this knowledge enormously. But even with all these future discoveries, some questions about the Kuiper Cliff may remain unanswered for a long time. The cliff is a feature that was set billions of years ago, either during the solar system's formation or very early in its evolution. The evidence for what happened has been partially erased by 4.5 billion years of subsequent evolution. Neptune's migration rearranged much of the belt. Collisional grinding destroyed some of the original population. Gravitational perturbations from passing stars and galactic tides have subtly altered orbits over billions of years. Reading the original signal through all this later noise is extraordinarily challenging. It's like trying to read a letter that was written 4 billion years ago and has been partially erased, written over, and water damaged in the intervening time. Some words are still legible, others are gone forever. And that, in a way, is what makes this story so compelling. The Kuiper Belt is not just a collection of icy objects orbiting in the darkness. It's a record, a frozen archive of the solar system's earliest history. Every orbit, every composition, every size distribution tells us something about the conditions that existed when the solar system was young. The cold classical belt preserves a fragment of the original protoplanetary disk, almost unchanged since the solar system's birth. The resonant populations record Neptune's migration, frozen into orbital relationships that were locked in billions of years ago. The scattered disk records the violence of gravitational encounters with Neptune. The detached objects hint at influences we don't fully understand. Perhaps a passing star. Perhaps an unseen planet. Perhaps something else entirely. And the cliff, that sharp, dramatic edge, where the classical population drops away, records a boundary, a limit, a place where something changed, where the conditions that allowed the belt to exist gave way to conditions that prevented it. Whether that boundary was set by the disk's own thinning density, by the erosion of small bodies over cosmic time, by the violent passage of a neighboring star, or by some combination of all three, we don't yet know. What we do know is this: the Kuiper Belt does not fade gently into the void. It ends, not with a wall, not with a visible barrier, but with a measurable, statistically confirmed decline in the population of objects on stable orbits. Beyond that edge, the outer solar system continues. Scattered bodies trace enormous ellipses. Detached objects drift through the darkness on orbits that take tens of thousands of years to complete. And farther still, at distances of thousands to tens of thousands of astronomical units, the Oort cloud wraps the entire solar system in a vast, spherical shell of icy remnants. The solar system doesn't end at the cliff, but the classical Kuiper Belt does, and that ending is one of the most intriguing signatures in our solar system's ancient history. We started tonight with a simple observation. The Kuiper Belt appears to stop. It drops off sharply beyond a certain distance, far more abruptly than anyone expected. We've traveled through the story of how the belt formed from the proto-planetary disk, how Neptune's migration rearranged it into distinct populations, how the cliff was confirmed as a real feature through careful surveys, and how competing explanations attempt to account for it. We've seen that the cliff is not a wall and not a total absence. Objects exist far beyond it, just not the stable, well-behaved classical population. We've seen that the explanations range from the physics of planet formation to the violence of stellar encounters, and that no single explanation has been conclusively proven. The outer solar system is one of the last great frontiers in our exploration of the cosmos. It's right here, in our own backyard, astronomically speaking. And yet, it's so distant, so dark, so faint, that we're only beginning to understand what's out there. The Kuiper Belt has already overturned our assumptions about the solar system's structure. It forced us to reclassify Pluto. It revealed the history of Neptune's migration. It showed us that the solar system's formation was far more complex and violent than we ever imagined. And the cliff, that sharp, mysterious edge, reminds us that the outer solar system still holds secrets we haven't uncovered. The next decade of astronomy will bring unprecedented discoveries. Tens of thousands of new Kuiper Belt objects will be catalogued. The structure of the belt will be mapped in detail we can barely imagine today. New detached objects will be found, testing the limits of our dynamical models. The Planet 9 hypothesis will either be confirmed or laid to rest, and the Kuiper Cliff, that enigmatic boundary at the edge of the classical belt, will finally be characterized precisely enough to distinguish between the explanations that have been debated for decades. But even then, some mystery will likely remain. The solar system is 4.5 billion years old. The events that shaped its outermost reaches happened in an era we can only reconstruct through indirect evidence, through the orbits and compositions and populations of the objects that survived. The Kuiper Belt is a time capsule, but it's an imperfect one. Some of its contents have been preserved beautifully. Others have been lost to the slow, patient destruction of cosmic time. Tonight, you've seen the outer solar system not as a barren void, but as a complex, layered, deeply structured region shaped by the physics of formation, the gravity of migrating planets, and possibly the passage of a wandering star. You've seen that the Kuiper Belt is not one uniform ring, but a collection of distinct populations, each telling a different chapter of the solar system's story. And you've seen that its most striking feature, the sharp outer edge, is not fully understood. This is one of those rare and precious things in science, a question that remains genuinely, beautifully open. The belt ends, we can see it end, we can measure the ending, but we cannot yet say, with certainty, what drew the line. And somehow, standing at the edge of what we know, looking out into the darkness of what we don't, that feels exactly right. The universe doesn't owe us tidy answers. Sometimes the most honest thing a scientist can say is that we're still working on it. That the story isn't finished. That the outer solar system, cold and dark and ancient, still has something left to teach us. And it will, if we keep looking.